At this point, we'll now move to today's plenary session, which will focus on ocean and atmosphere observing needs. So these are our disciplinary sessions. And Jim Edson of Woods Hole Oceanographic Institute will be our moderator. So thank you, Jim.
You're welcome, Charlotte. Today's theme will be on atmospheric and oceanic observing needs in the tropical Pacific. And it is indeed my pleasure to introduce two very successful young scientists to our audience. First being Dr. Yassir Eddebar, and the other being Professor Kathleen Skiro. I hope I'm pronouncing that correctly. So Dr. Eddebar is a postdoctoral scholar at the Center for Climate Change Impacts at the Scripps Institution of Oceanography. I think I've heard of Scripps. Yeah, I've heard of Scripps. He has a wide range of research interests that include carbon and oxygen cycles, biogeochemical and physical dynamics, and climate change. Now, Professor Skiro is a highly published assistant professor in the Department of Environmental Science at the University of Virginia. She also has a wide range of research interests that include atmospheric convection, tropical dynamics, cloud processes, and regional climatological studies. Now, I just want to make it clear, although their research is clearly not limited to one boundary layer, their talks will focus on first the tropical ocean and then the tropical atmosphere. So without further ado, I'd like to begin the session with the oceanic planetary talk given by Dr. Eddebar, and it's going to be on biogeochemical and physical observing needs for the tropical Pacific Ocean. So take it away, Yasser.
So thanks, Jim, for the introduction, and I'm really glad to be talking to you today about the intersection of biogeochemistry and physics. 15 minutes is not enough to talk about both worlds, and so I'm going to focus on the interaction between the two. And so what I thought I would start is where we left off yesterday, and this is a point that Samson had mentioned in the review. And it's a comment from Ariane Verdi on biogeochemistry and how little we talk about it in discussions about ocean physics, about the tropical Pacific in general. So she raised an important point that we don't talk about BGC because it's got strong vertical gradients. Tracers like oxygen and carbon can add an independent or strong constraint on vertical mixing and upwelling. And they can also be really useful for physical and biogeochemical modeling and data assimilation. But there wasn't a whole lot of discussion after that, although Billy Kessler was a big fan of the idea. And so I thought to maybe focus on this point for the rest of today and hopefully raise some questions for the workshop and the community to think about, not only just for this workshop, but moving forward. So one question, usually when we think about ocean physics and biogeochemistry is, what can ocean physics do for biogeochemistry? How can enhanced physical observations be useful for biogeochemistry? What kind of sensors can we put on Argo floats, for example? And that might not be the best way to approach this problem. And another question is, what can ocean biogeochemistry do for physics? And usually we're interested in how chlorophyll or biology, for example, modulates the irradiance in the surface layer. And that's also really useful. But I think what we might be missing out is another opportunity here is what can we learn from measuring and modeling ocean biogeochemistry and physics in concert. And so I don't know the answer to that question. I'm just kind of posing it for the community to think about. But some ideas for what we might be missing out on are ventilation pathways, vertical mixing, model biases, constraining circulation and data assimilation model, stratification, as Chris had mentioned earlier, ensodynamics and submeso-scale dynamics. Imagine what we can constrain or think about when we look at biogeochemical distributions and physical parameters in concert. And this is not new. Cromwell, in one of the pioneering studies on tropical Pacific oceanography, when he was looking at upwelling in the equatorial Pacific, The first sentence of his abstract used oxygen and phosphate along with salinity and sigma theta to show evidence of upwelling near the equator. And particularly oxygen, where there is lower oxygen near the surface, that gave him some hints on some of this upwelling occurring. And he sort of explained it through Ekman dynamics and so on. Klaus Wertke was another big fan of using ocean biogeochemistry alongside with temperature, salinity, and velocity to give a full picture of the meridional and the vertical structure of the flow of the tropical Pacific. So what are we missing out? What can we see in the tropical Pacific from both physics and biogeochemistry? One, there's been a lot of discussions today on ocean deoxygenation. So the ocean is losing oxygen, and the equatorial Pacific is losing oxygen at some of the highest rates in the global ocean. So it's contributing to about 20% of oxygen loss globally. And the models also show that there should be oxygen loss in the global ocean in response to ocean warming, but they disagree pretty widely in the tropics. Particularly in the tropical Pacific, some models predict that there will be an increase in oxygen, while others predict there will be a decrease. And of course, the models have some large biases in representing not only oxygen, but also circulation. But the observations themselves are very sparse, particularly in the tropical Pacific and along the equator, where we have values of about 20 to 50% of temporal data coverage. And then finally, our process understanding of oxygen dynamics and how it relates to ocean circulation is pretty basic. So there's some work by Liz Drunkard and Karnauskas that shows that there's been a strengthening of the equatorial undercurrent in the ocean reanalysis, which should lead to oxygen increase in the equatorial Pacific over this region, but instead we see an oxygen loss. So, so there's some discrepancies here in our process understanding of the oxygen budget and other parts of ocean biogeochemistry. The EUC, for instance, is a major source of nutrients to the Eastern Pacific, and that might modulate respiration and productivity in ways that can lead to oxygen loss. And then finally, as an ocean biogeochemist, trying to reach out to the physical oceanography audience, if these trends are real, what can they tell us about the ocean circulation response to atmospheric forcing? And by atmospheric forcing, I mean changes in the winds, ENSO state, or changes in radiative fluxes. So the CHIPAS report has a set of recommendations. I'm describing them here in two different sets of recommendations. One had to do with sustained network. And so some of the recommendations that Sophie Cravat and others detailed yesterday is that we need enhanced vertical and meridional resolution of the current profilers, perhaps an increase in the depth range of the current profiles in the equatorial, the mooring arrays, alongside with temperature and salinity. But we also need biogeochemical measurements. And so one of the recommendations is to enhance BGC Argo flow coverage to about 124 floats from 10th south to 2 north, and enhance biogeochemical coverage by reinstating CTD casts along the maintenance ships that maintain the TMA array. But that's not enough. I think we need some additional measurements that can fill in the gap. And there's a pilot study described in the latest report that's currently in review to evaluate prowler moorings, for example, with oxygen sensors and current meters and ADCP to get an idea of the variability in the EUC and its transport, and perhaps link that to the Eastern Pacific OMZs and some of the moorings that exist there. We also need integrations of observations and models, and I'm proposing as well here that we could think about other pilot studies like gliders with oxygen sensors that can complement the prowler lines, or perhaps having an oxygen sensor on one of the super sites that Sophie was describing yesterday. And then in time, perhaps adding oxygen sensors on the Tau mooring array. And that could be useful for example, constraining the variability in the OMZ. Another major observing need is the ocean biogeochemistry and its relationship to climate variability. And we'll hear more from Sarah Schluniger and Capotondi, Croning. And that's natural variability challenges the attribution of carbon and chlorophyll variability, but also physical variability. And the PCO2 measurements from Feely shows some large variability in surface PCO2 that's tightly related to ENSO, as well as to the decadal variability in the tropical Pacific. But that variability is still poorly constrained, and some major uncertainties relate to local variability driven by ENSO and other air-sea interactions versus remotely forced variability. For example, the increase in PCO2 and the corresponding acidification of the surface ocean has been shown to actually be in part driven by remote sources from water masses from the mid-latitude and higher latitudes that bring in anthropogenic carbon back to the surface through the EUC. So an observing challenge is poor subsurface sampling of BGC and spatial coverage for PCO2. And then again, here, the enhanced biogeochemical Argo float is going to really help in that regard. But some pilot studies to enhance the PCO2 coverage along the ship mooring lines would be quite useful, I think, in giving us a full picture of how the surface variability in PCO2 relates to higher latitude sourcing. Some additional pilot studies, perhaps to show, to add more PCO2 further west in the equatorial Pacific. But one last piece of or advance in science in recent years is the role of mixing for biogeochemistry. And we've heard yesterday from the recommendations summary from Samson and Chris that mixing plays a big role for ocean physics, and that's still poorly constrained. For BGC, it's very rudimentarily understood, and some work from Levy et al. Shows that mixing might play a critical role in the future advance of ocean deoxygenation. And this is subduction of, or diffusive subduction of oxygen into the thermocline might lead to a big portion of the oxygen loss in the future. We're currently starting to look at the biogeochemical imprint of some of these mesoscale eddies and mixing processes. But mesoscale or eddy resolving models are telling us that tropical stability waves and the vortices that are embedded with them are expected to drive a substantial change in the biogeochemical distribution of the equatorial Pacific and drive quite a lot of variability across timescales. And the processes themselves are pretty complex and interact across timescales and spatial scales. So the challenge is that the sustained network is not well suited for high frequency variability associated with these waves. And the models, the global models, don't simulate them well. And we're starting to understand that the same processes that impact heat fluxes and the heat budget in the equatorial Pacific from the pump study also have a major impact on oxygen distributions. Here, for example, mixing is an important term for oxygen variability and structures. And so for a process study, perhaps we can think of expanding the pump framework to include biogeochemical tracers. That's not from a selfish point of view. I'm interested, for example, in what these waves do to biogeochemistry, but we could think about what can biogeochemistry tell us about mixing processes and upwelling associated with these mesoscale eddies. And so perhaps we can think of a tropical stability wave experiment with biogeochemical sensors in the future, and maybe instead of using a ship-based study, perhaps we can make use of the various advances from autonomous surface vessels and underwater vessels like gliders with oxygen sensors, as well as a supersite perhaps at 125 West or 140 West. Or perhaps we can enhance the sustained network in a region near these waves where we can take a more representative observational estimate of these waves as they're passing through. And so one question perhaps for today's later panel discussion is, what can these measurements of oxygen and CO2 tell us about mixing and upwelling and air-sea interactions at the mesoscale? And then finally, the observing needs. We need observations to be integrated in models. And one challenge with understanding the variability of oxygen minimum zones is essentially how can we identify these processes across different timescales. And so we need graded products and data assimilation of growing physical and biogeochemical data sets to be presented in a useful format. And I think some of the data assimilation products, for example, from Ariane Verdi in her poster, and perhaps a panel discussion tomorrow with Matthew Masloff, can tell us a bit more about how we can make best use of the observing network and how the network can be integrated with these data assimilation methods in a more successful manner. And then we need process studies that combine observations and models to gain a better understanding of the variability from seasonal timescales to interannual variability associated with ENSO, and also on long-term timescales. And this is a simulation of the MIT GCM that shows some significant interannual variability in oxygen at 200 meters, but also just the structure of the OMZ changing with the heaves of the isopycnal, with the delivery of oxygen by the EUC and the other zonal jets, and also perhaps a long-term trend in oxygen that we can provide an important constraint using models here. And so the range of processes that are impacting biogeochemical and physical variability across these different timescales are interacting at all times. And so turbulent mixing, for example, is modulated by tropical instability waves. Submesoscale features are also interacting or also take part of tropical instability waves and tropical instability vortices in modulating biogeochemistry. And TIVs themselves interact with Kelvin waves and equatorial upwelling. And then the impact of anthropogenic warming can change how these smaller scale features can have an impact on BGC. And so when we're trying to understand the interaction between these processes, I think we want to go with a multi-platform approach. And a question that I want to leave everyone here today with is, while we're doing that, what can we learn from measuring and modeling both ocean physics and biogeochemistry across these scales? And with that, I'll open it up for a question, and sorry for going over time here.
Okay, very good. So we have a few questions from chat. The first one here from Billy Kessler. What is the required sampling time scale for oxygen profiles? Do you need moorings, which are sort of 1 hour or less sampling, or could you use the BGC Argo, which is sort of 10 days? Is that good enough?
Yeah, great question, Billy. So it depends on the process that we want to think about. If it's tropical stability vortex passing through, we might need hourly, daily frequencies of oxygen measurements and PCO2, and the moorings on 125 West and 140 are already showing some interesting signals in PCO2 at the surface at 3 hourly frequencies. So 3 hourly would be great for getting an idea of some of these high frequency phenomena. For ENSO variability in the seasonal cycle, I think the spatial coverage of BGC Argo is going to give us a great constraint on the oxygen budget alongside with data simulations. And so I think that different networks, BGC Argo and moorings, will allow us to divide up what frequency we need. But I think for some of these high frequency measurements, I think moorings, both in the Eastern Pacific and hopefully in the Central Pacific, 3 hourly to daily timescales would be really useful.
I'm going to ask one more spatial question from Daoshang. If you could measure oxygen at only a single level, where would it be? And if you actually need profiles, what's sort of the minimum resolution you would need?
Huh. I don't know if I can answer that question objectively. I think for the moment, I believe the Eastern Pacific is a good place to start. I think we'd want to measure oxygen at least in a few different places. But 95 West, where the Proler study in the third report is a good place to start. And I would say one good place would be the interface between the mixed layer and the thermocline, so somewhere between 50 and 100 meter, to get an idea of how much changes in the oxygen supplies happening both from upwelling and the EUC. But I think we want pretty high frequency measurements from in the upper 300 meters in that region. I think the Proler lines right now in the report are only recommended for 200 meters, but I think we would want up to 500 meters for a range of moorings to get an idea of how the EUC and the tropical stability waves and other jets are influencing the boundary of the OMZ as it's expanding or shrinking. So again, I thought I probably won't answer that question objectively.